Welcome to Math with Malia. Today we're doing Savvas enVision Algebra 1, Topic 6, Lesson 5, Geometric Sequences. After this lesson, you'll be able to identify and describe geometric sequences. So think back to Topic 3 when we did arithmetic sequences in our linear functions unit. This is going to be similar, except instead of adding a number over and over again, we're going to be representing something that looks similar to exponential functions. In the Explore and Reason, we have this diagram of stadium seating, and you can see in row A, we can call this row 1, okay, and row B or 2, 3, 4, and 5. What's the total? Well, we have 2, and what is changing as we go into each row? Okay, so going from 2 to 5, we're adding 3. Does that work each time? Are we adding 3? 2, 3, 4, 5. Yep, we added 3 each time. So each time we go to a new row, we are adding 3 seats. So again, we're going to think about sequences. If we're adding over and over again, that means our common difference, or D, is going to be 3. So how did we write our arithmetic sequences? We can write it two ways. We can show the recursive formula or the explicit formula. So the recursive formula would show us any number in the sequence, and I would have to know the previous term, the one before, the n-1 term, and then I'm going to add the pattern. So that could be our recursive formula, but that's not always helpful when we're trying to figure out how many seats will there be in the 12th row. So let's write it as an explicit formula. To write the explicit formula, to know the nth term, we have to take the previous term, or the first term, and then we're going to add the common difference times n-1. If you remember why we multiplied by n-1, because we don't apply the common difference to get to the first row. The first term, we haven't applied the common difference. Like if I start at 0, I haven't added 3 yet to get to the first term. So we're just going to say the first term, then multiply the common difference by n-1. So now let's just substitute values for what we know. Okay, so to get the number of term, we take the first term. So what is the first value in our sequence? The first value in our sequence is, how many seats do we have? We have 2. Okay, so that's like the number of seats in the first row. And the common difference we know is 3, and we're going to multiply by n-1. And if we simplify that, we do some algebra, we'll get 2 plus 3n minus 3. That simplifies to be 3n minus 1. Part C, row Z of section 12 must have at least 75 seats. Okay, if it's row Z, what letter in the alphabet is that? Well, that's 26, right? So if we say N is 26, because that's Z is the 26th letter of the alphabet, then we just plug that into our formula. We're going to evaluate A of 26. Okay, so 3 times N minus 1. And if we do 3 times 26, we get 78 minus 1, so there will be 77 total seats in row Z. That is at least 75. So how are geometric sequences related to exponential functions? We're going to get there. First, we're going to review geometric sequences, what they are, how to write the formulas, and then we're going to see how they're tied to exponential functions. Identifying whether a sequence is arithmetic or geometric. I said this in the beginning. If it's arithmetic, we're going to be adding or subtracting as a common difference. So you can think arithmetic, we're adding and subtracting. That's what you do in elementary school. Geometric, when you're doing geometry, we're looking at area or volume. We are multiplying things. So our operation that we're using a lot is multiplication or division. Okay, so that's a geometric sequence. We are looking for a common ratio. I hope that sounds familiar. We have common ratios in exponential functions. So to look at a sequence, you just need to decide what is the pattern to get to each next term. So part A, what do we do to get from 3 to 2, and then 2 from 4 to 3? Well, if we take the second term and divide it by the previous term, so going left to right, I'm multiplying. And so then if I reverse direction, I need to reverse the operation. That means I'm going to divide the second term by the previous term, the one before it. And if we do that, we can see 4/3 divided by 2, 4/3 divided by, or 8/9 divided by 4/3, 27 divided by 8/9. We get a common ratio. We're multiplying by 2/3 each time. Okay, so we multiply by 2/3 each time to get to the next term in our sequence. So this is geometric. Let's look at part B. What am I doing? Well, do the same thing. What's the pattern going from the first to the next one? Well, I add 1.5. I add 1.5, I add 1.5. So since we are adding over and over again, this is a common difference. So therefore it is arithmetic. Our pattern is adding or subtracting. Try it number 1. We're going to describe the sequence as arithmetic or geometric and why. So looking at part A, what do we do to get from 1 to 2.2? Well, we could say we add 1.2, but does that work going to the next one? No, adding 1.2 would not work. So we must be multiplying. What do we multiply by? Hopefully it's 2.2. So you can check. Make sure you can multiply each term by 2.2 to get to the next one. You'll want to check that because sometimes there might be a term at the end where the pattern doesn't work. And so then it can't be a sequence or a geometric sequence. So part A is geometric, and we know because we are multiplying by 2.2 each time. Part B, well, are we multiplying by 75 each time? Doesn't look like it. We are adding 74. You'll want to check. If you add 74 to each previous term, do you get the next term? Yes, in fact, we do. So this is arithmetic because our common difference is 74. Example 2, writing the recursive formula. So remember the recursive formula, that keyword is recursive. We have to know what comes before. It's happening over and over again. It is recurring. So this one tells us the pattern, but we have to know the previous term. Remember that was written by a to the n minus 1. So we have to have the previous term in our recursive formula. Here's our sequence, 8, 12, 18, 27, 40.5. So first we have to figure out what is the pattern that we're doing. If we go from 8 to 12, we can figure out we are multiplying by 3/2, and we can check to see if that works each time, and it does. So our common ratio is 3/2. And when we're writing our recursive formula, we're going to call that R, not D, because that stood for common difference. This is going to be R for common ratio. So R is 3/2. And then instead of adding it to our previous term, so I'm going to show you the arithmetic recursive formula. You take the previous term and then you add the common difference. That's our arithmetic recursive formula. Instead of adding the pattern, we're going to multiply the pattern, right? So it just goes in front like a coefficient. So we multiply the pattern or the common ratio by the previous term. So then we do that. We just substitute R for 3/2. And we get our recursive formula. We have to define the first term whenever we write our recursive formula, so make sure you define what the first term in the sequence was. And in this case, our A1 term is 8. Try it number 2. Let's write the recursive formula for this sequence. So they've told us it's geometric, then we're looking for a pattern where we are multiplying or dividing. Looks like we are dividing, okay, or we're going to be multiplying by a fraction less than 1 because our numbers are getting smaller. Okay, so maybe look at the end. What do you do to 48 to get to 12? We divide by 4, which means we're multiplying by 1/4. Go ahead and check at the beginning. If you do 3,072 times 1/4, do you get 768? Yes, you do. So R is 1/4. Our common ratio is 1/4. Let's write it in our recursive formula. So to get to any number term, we take our common ratio and we multiply it by the previous term. So again, recursive formulas, we can just look at it and identify the pattern. But we do have to know the previous term, and we have to define what the first term is in our sequence. So where do we start? We start at 3,072. Example 3, what is the 10th term in this sequence? So it's the same sequence that we had before. Okay, so we know our common ratio is 3/2. And now we're looking for a 10th term, a specific number of term. So if you remember our arithmetic sequences, to get to any number of term, if I want to use an explicit formula, then we would take the first term and then we would add the pattern, the common difference, times n minus 1. Remember, this is previous to our example with the stadium seats. We multiplied by n minus 1 because we don't apply the pattern on the first term, on the first number in the sequence. That's where we start. So it's going to be similar to this. We have to know where to start. We have to know the first term, and then we're going to multiply our common difference. Okay? Except since we're multiplying over and over again, what operation is that when we are multiplying over and over again? Well, that's going to be exponential, right? So now our n minus 1 is going to be in the exponent, and I hope you see something looking familiar here. So we're going to take our first term, multiply it by the common ratio, and our n minus 1 will be in the exponent. The number of term will be in the exponent. So now we can evaluate a of 10. That means n is 10. What's 10 minus 1? It's 9. And you can just plug this into your calculator. Try it number 3. What is the 12th term in this sequence? So that means n equals 12. The initial condition is 3. That means the first term is 3. And then they gave us the recursive formula. So can we figure out the explicit formula from this recursive formula? Well, remember, the recursive formula tells us something very important. We can just look at it and see the pattern. So what's the pattern? What are we multiplying by? We are multiplying by 6. So our common ratio is 6. Now we have all the pieces and the values that we need in order to write our explicit formula. So our explicit formula would be any number term equals the starting value, the first term, 3, times my common ratio, 6, to the n minus 1. Because again, I didn't multiply by 6 on the first term. I haven't done that yet. We don't apply the pattern until we go from first term to second term. So now let's evaluate a of 12. 3 times 6 to the, what's 12 minus 1? 11. And if we type that into our calculator, make sure you put 6 in parentheses, and then you do caret 11 on your calculator. We would get this big number, 1,088,391,168. Example 4. Now we're going to connect and see the relationship between exponential functions and geometric sequences. We saw how similar the formulas were. We saw how our input or our term number is going to be in the exponent, just like an exponential function. So here's our situation. We have a podcast, and in the first week they had 5 subscribers. And it says the number of subscribers doubles each week. So if we're doubling over and over again, we know we are doing 2 to the x, right? We have an exponential function. And so if we remember our basic formula for writing an exponential function, we take the initial value, which is 5. So in this case, they're saying the first week, you could think of it like at the launch. So at the launch, they had 5 subscribers. So we're calling 5 subscribers the initial value. And we know our constant ratio is 2. We're multiplying by 2 over and over again. And then our x goes in the exponent. If we were to graph this, we can see that it does have that exponential curve, okay? And so our pattern is multiplying over and over again. If we are doubling, or our common ratio is 2, so we could say r equals 2, then can we write this as a geometric sequence? So we would put it in the same formula. What's our starting value? Our initial value is 5, or our value at week 1, our first term, week 1. And then our common ratio is 2, and then we do n minus 1. Let's double check to make sure this is right. So the first week, we know we had 5 subscribers. So that means n is 1. If n is 1, what's 1 minus 1? It would be 0. So then we would have 5 times 2 to the 0. 2 to the 0 is 1. So then that would just be 5. Does that make sense? when n equals 1, during the first week we had 5 subscribers. Yes, it works. So we could also write this as a geometric sequence, but notice instead of x, our input is n minus 1 because we're calling our input the number of weeks. It's not saying 5 is at week 0, 5 is at week 1. Okay, so technically it's not the initial value, it's the first term in our sequence. So how many subscribers will we have in week 9 if the initial number of subscribers is 10? So A1 is 10. We're still doubling, so our common ratio is 2, and we want to evaluate A of 9. So our formula would be whatever term, whatever week, the initial value is 10 times our common ratio. What's our common ratio? 2. And then it's always going to be to the n minus 1 because we, again, going from 0 to 1, did we multiply by 2 yet? We haven't multiplied by 2 yet. Okay, so we always do it 1 less than the number of term. We apply the pattern 1 less time. So if we're going to evaluate A of 9, then we're going to just substitute into our equation. 9 minus 1 is 8, so we'd have 10 times 2 to the 8, and we could type that into our calculator, and we would have 2,560 subscribers in week 9. Example 5, another application problem. We have people attending this festival, International Food Festival, and attendance decreases by 20% each year since the first year. So less and less people are attending this festival. It's decreasing by 20%. So let's think. This sounds similar to exponential decay. I'm decreasing by a percentage. Okay, I'm not decreasing by a constant rate. So if we're losing 20% each time, that means we start with 100 or 1 and we're subtracting 20%. So our actual multiplier is 0.8. You could also think of it as we are keeping 80% of the previous year, right? If we're losing 20%, we're still keeping 80%. So we're going to do 80% times the previous year over and over again. So writing that into our recursive formula, if we know the previous year, that's the a to the n minus 1 term, we're just going to multiply it by 80% or 0.8. So here's our recursive formula. And if we know the previous term, well, we do. They gave us the previous year. So our n minus 1 term is 12,550. So we could figure that out. We could do 80% of 1250 and we'd get 1,000. Then we could do 80% of 1,000 and we'd get 800. Then we could do 80% or 0.8 times 800 and we get 640. And then we would do, okay, do you see what I'm doing? I'm multiplying by 0.8 every time. And then 80% of 640 multiplied by 0.8 again, and we would get 512 for the 5th year. So we could work that out, or we could just write the explicit formula. Okay, so if it's just a few terms down the line, using the recursive formula can be fine. Let's write the explicit formula then. So we need to know the first year in order to be able to write the explicit formula, okay, to find year 10. So we're going to say this is the first year, the first term, and then we're going to go 10 more terms down the line. We've already gone 5. If you want to multiply by 80% 5 more times, you can, but let's write the explicit formula. Remember, we're going to be having our exponent be n minus 1, so we just plug in the values. Our first term is 1250. Our common ratio is 0.8, and we're going to do n minus 1. In this case, 10 years, so n equals 10. What's 10 minus 1? It is 9. So here's our formula we're going to type into the calculator. And we can do that. I'm not sure why they did 4/5. I would just do 0.8. I really don't know why they changed it to 4/5. But you can type this into your calculator. Okay, it'd be a star times parentheses. Make sure you put the 0.8 in parentheses, and then you would do your caret for the 9, and you would get this value. So we could round, since we're talking about people, we can't have a decimal amount of people, so let's round up, and we get about 168 people. The formula a of n equals 1.5 times a to the n minus 1. So this is our recursive formula, right? It tells us we have to know the previous term, but I can identify the pattern right away. What am I multiplying by over and over again? I'm multiplying by 1.5. Okay, so I'm just going to write that right now because I know that. It has an initial value of 40. That means a of 1 equals 40. Use the explicit formula to determine the fifth term. So now I'm going to look for a or when n equals 5. So first, let's write the explicit formula. A of n equals my first term, which is 40. Okay, I'll write it up here again so we remember. A1 times r to the n minus 1. A1 is 40, our first term is 40, times what is our common ratio? We're multiplying by 1.5. I know that from the recursive formula, that's why those are helpful. And then I'm going to do 5 minus 1 in my exponent. Okay, and we multiply, 1.5 to the fourth, type that into your calculator, and we would get 202.5. That would be the fifth term in a sequence following this pattern. Here's the concept summary for geometric sequences and how they're related to exponential functions. You can see that we do have an exponent. Our input isn't in the exponent, so it is similar. Make sure you review the difference between explicit formulas and recursive formulas and how to write them. But really, it's just looking for the common ratio. What are you multiplying or dividing by over and over again? If you have any questions, put them in the comments. Make sure to like and subscribe. Come back for lesson 6.